So to show that the equivalence class is the same thing as the coset, that's what this says here, okay? We have to show that this is a subset of that, and this is a subset of that. Right? So we have to prove these two things. All right. So from here to here is the proof of this first one, and here is the proof of this second one. Right? Now, how do you prove that something's a subset? Well, by showing if X is any member of this, therefore X is a member of that. And if that's the case, for all X belonging to this, then for all X belongs to that, that's the definition of a subset. So let's try to show that if any X belongs to that, it also belongs to that. And similar logic for here. All right. So let X belong to this one, and let's see what we can deduce. Well, look, if X belongs to the equivalence class, remember that's a subset of all the elements that are equivalent to A. So if X belongs to that class, that subset, then this is true. Right? That's the definition of this. It's the set of all these X's where that's true. So X is equivalent to A. Well, if X is equivalent to A is equivalent to X, right? Because this relation here is an equivalence relation. So it has those three properties: reflexive, symmetric, transitive. Right? So here we're using the second property of symmetry. Right? Now, if A belongs to X, if we use C here, now remember this is all in the context of the equivalence relation here being this. Right? That's given. It's all in using that particular kind of congruence relation. This tilde here. All right. So using C, if that's true, then A inverse X belongs to H. That's using this. All right. Now, so we've got this. Now using 46.2, so now it goes both ways, right? It's an if and only if. So if that's true, that's true. Now we've got that, therefore we can deduce AH equals BH. Well, we're talking X's now, so AH equals XH. So we've got that. And now using 46.1, so we've got AH equals XH, and now use 46.1. So AH equals XH, then A and X are in the same coset. Right? There's an if and only if goes both ways. So we've got AH equals XH, therefore A and X are in the same coset. So A and X are in the same coset. Okay? But we know that A belongs to AH. Right? Any element belongs to its own coset. Now, why is that true? Well, H is a subgroup, right? It will contain the unit. And so inside this subset, you will have AE, which is just A. Therefore, A belongs to that subset. So A belongs to EA, right? Well, if A belongs to AH, and AH is the same as XH, that means that X belongs to AH. Right? Can we say that again? Now A belongs to its own coset. Right? A belongs to its own coset. But AH is equal to XH. Therefore X, if A belongs to AH, and A or X in the same coset, therefore X belongs to AH. Okay? Alright. So we've now shown that X belongs to AH. So, summarizing a bit, if X belongs to A bar, X belongs to AH. For all X belonging. Okay? Well, that's the definition of a subset. So if x belongs to A bar, that implies that x belongs to A H. So from that, you conclude this is a subset of that one. Okay? So A bar is a subset of AH. Right? So that's halfway there. Now let's go the other way. Let's assume x belongs to AH. So we're going to try and show that this is a subset of that one. So for any member, any x belonging to this, then that x will belong to this one. So let's start with x belonging to AH. So let x belong to AH. Now we know that A belongs to AH. Right? We did it here. We know that A belongs to AH. Now if x belongs to AH and A belongs to the AH, that means x and A are in the same coset. Right? They belong to the same coset. This is a coset. AH is a coset. So x and A both belong to that same coset, AH. Okay? So we've deduced that x and A are in the same coset. They belong to the same coset. Now we can use 46.1. 46.1. A and B are in the same coset. A and X. So now there's an if and only if, so we can go from the left to the right. And so that means that AH equals XH. Okay, so we can deduce X, or AH equals XH. Right, so we have that. Now using 46.2, XH equals 46.2. So AH equals XH, and then we can go from the left-hand side to the right-hand side. This is an if and only if. So that means A inverse X belongs to H. Where are we? So yeah, so A inverse X belongs to H. Okay, so now we've got that. Now using C, A inverse X belongs to H and C. A inverse X belongs to H. Therefore A is equivalent to X. A is equivalent to X. So A is equivalent to X. Alright? Now if that's true, X belongs to A bar. Right? By definition, what is this A bar? It's the equivalence class, right? It's the subset of all elements that are equivalent to A. Right? So if A is equivalent to X, X is equivalent to A. Right? So therefore X belongs to this equivalence class. Alright, so if X belongs to AH, X belongs to A bar. Therefore, AH must be a subset of A bar. Right? AH is a subset of A bar. Well, you put these two results, that's why I put them in rectangles, you put these two results together, the only way they can be compatible is if these two are equal. Right? So you have shown for the case when the equivalence relation is of this form, which is of this form, in that special case, then your equivalence class is actually equal. It's the same subset as your coset of A, the little element A. Right? Okay, so that's the end of that extraordinary story. Okay, now something new, relatively. It's another example of an equivalence, which I've shortened to just EQ or EQIV, of an equivalence relation, but introduced here because it's a good spot to do it, because we're talking about examples of equivalence relations and equivalence classes and such like. Right? This is the topic for lecture 16, chapter 16. Right, now this particular example we will meet again in the final chapter of the book, hence the course, chapter 19, so it's three lectures away. Okay, in theorem 64 when we get to it. Now it involves functions, just mappings between one set and another. We've done a whole chapter on functions. Okay, so just an ordinary function which maps set x into set y. Okay, so imagine you have two elements belonging to x, just a and b. Now, there's an equivalence relation defined on these elements of X. So here's your equivalence relation, and the definition is A is equivalent to B if f of A equals f of B. Okay? So in effect, what you've got is like you've got a many to one mapping